Hello, and welcome to today's webinar, Transient Simulation Workflow for a Battery Thermal Runaway Event. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Dennis Hintz. Dennis is a thermal and CFD engineer at Thermal Analytics who performs modeling and numerical simulation for automotive applications. He started at TAI in 2020 and focuses primarily on cabin and HVAC modeling. Dennis specializes in the development of cabin simulation methodologies, facilitating advanced coupling between software tools and human comfort modeling. He values strong attention to detail and the importance of capturing the relevant physics while making the optimal modeling assumptions. Dennis holds a BSE degree in chemical engineering from the University of Michigan and a PhD in chemical engineering from the Illinois Institute of Technology. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. And we're also recording this webinar and we'll be sending you the link following this presentation. And with that, Dennis, if you're ready, you may begin.
Okay, thank you very much, Chris, for the nice introduction, and thank you everyone for your time attending today. The title again of this webinar is a transient simulation workflow for a battery thermal runaway degassing event. So we'll begin with an introduction to thermal runaway. We'll define the problem and the motivations. We'll discuss some common runaway simulation workflows. And then we'll narrow our focus a bit to the main topic of this webinar, which is the transient heat protection and venting workflow. We'll demo the process workflow that's been developed. We'll look at some benchmarking results, and we'll show how we can use this workflow for thermal protection and safety analysis. And we'll look at the benefits of using Tytherm for subsequent rapid thermal design studies. And we'll close with a brief look at some alternate heat protection workflows, and then open it up for Q&A. So another common theme here for this webinar, especially when we're talking about these alternate workflows, is the extension of common internal combustion engine heat protection workflows to the electric vehicle. So we have a long history here at TAI of performing underhood and underbody analysis for ICE vehicles. And along with that, over the years, we've developed a wide array of heavily validated simulation workflows in heat protection. And the reason there's so many is that because these workflows range, all over the classic spectrum between accuracy and computational time. So each one is the optimal solution for the specific customer. So the theme here is that it turns out that a lot of these workflows are also applicable to the EV for thermal runaway. So thermal runaway is basically a runaway exothermic reaction inside the battery cells. So thermal runaway can occur under conditions when the rate of heat generation in the cells is higher than the rate of heat dissipation. And if these conditions persist for some time, the cells can achieve temperatures that sustain this runaway reaction, and the reaction can propagate from cell to cell within the pack. So there's a variety of abuse scenarios that can cause these high temperature conditions. So there's electrical abuse, things like overcharging, there's thermal abuse, so poor thermal management either during operation or during charging, and then finally mechanical abuse. So things like collision or aging resulting in failure of certain components, and for example, maybe causing a short circuit. There's a number of exothermic reactions that contribute heat to the cells during thermal runaway. And on top of heat, they also contribute things like combustible hydrocarbon gases, oxygen, and electrolyte decomposition, for example, greatly increases the risk of short circuit, and this can release a lot of energy into the cells very quickly. So at this point, the risk of fire is very high. At the lower temperatures, the potential for thermal runaway mitigation and control is much higher, but up here, up at these elevated temperatures, fire inside the pack and propagation occurring, the goal really is to provide enough time for the occupants to escape safely and also maximize the safety of first responders and safety personnel. So here on the right, you can see a video showing the aftermath of such a thermal runaway event. So beginning with degassing underneath the vehicle, dark cloud of vent gases, and particulates, eventually jet-like flames, and a fire that ultimately consumes the vehicle. So while the risk of battery electric vehicle fire is lower than the ICE vehicle, the outcomes can be devastating, and the onset of runaway is unpredictable. So the bottom line is that battery thermal runaway events pose significant risks to vehicle occupants and first responders as well. It's for this reason that recently there's been a strong push globally for the international harmonization of safety regulation. And that's being driven by the United Nations, with the global technical regulation for electric vehicle safety. This is currently in progress. So nations are conducting research and discussing research about optimal testing parameters and safety criteria for thermal propagation, fire resistance, warning requirements, etc. China has already adopted their proposed solution for the global technical regulation, which is a 5-minute egress time. So essentially requiring a delivery of a warning to the occupants at least 5 minutes prior to a hazardous situation in the cabin. Of course, this also means no fire or explosion within the cabin for at least 5 minutes. And importantly for us, a so-called thermal propagation test, among others, was introduced. So this is just to ensure that these safety criteria are being met during development. The EU has recently passed the EU battery regulation, and among many other things within this regulation, they've agreed to adhere to the safety parameters defined within the UN global technical regulation as well. So this means, similar egress time and propagation tests and other safety tests will be defined as well. In the US was also heavily involved in the UN global technical regulation discussions and still is. And currently a proposal is being developed based on phase 1 of the global technical regulation for submission into the federal motor vehicle safety standards. So EV and battery safety regulations are coming very soon and globally. And these standards are expected to drive our simulation needs going forward. So based on these safety standards, there's a few different simulation workflows that we're interested in. The first one is mitigation. Here we're trying to actually simulate the onset of thermal runaway. So identifying prevention and mitigation strategies, we're looking at optimizing the battery design, the battery management system, and the battery thermal management logic. We're looking at optimizing structural design in the event of collision or mechanical abuse. We're identifying the optimal early detection and warning mechanisms for thermal runaway. And the difficulty here with these types of analysis is this is really probabilistic and stochastic type of analysis. We're trying to estimate and limit or decrease the probability of the onset of thermal runaway over the life cycle of the battery pack. The next is propagation. We're actually trying to resolve the physics of propagation within the battery pack. So the propagation of thermal runaway from cell to cell within your battery pack. The objectives here are to optimize the battery design. So slow down runaway propagation or stop it completely early on within the onset of runaway. We're looking at things like cell spacing, so the thermal resistance, heat capacity of heat sinks, insulation between the cells and within the pack, and cooling techniques for after the onset of thermal runaway has been detected. And finally, the focus of this webinar is heat protection and safety. So here we're trying to simulate the result of the worst case thermal runaway event on the vehicle exterior. And the key difference here is that we're not necessarily trying to resolve all of the propagation physics, right? We're not trying to compare different rates of propagation. The assumption is that we understand our worst case scenario, we understand the propagation behavior of our pack, and we can apply that then to focus on the exterior of the vehicle and the cabin, for safety of the occupants and first responders. Okay, so as I mentioned, that's the primary objective here, to meet these egress and safety criteria targets. So we're looking at, temperature limits of various components with the focus of heat and thermal protection. And we're looking at controlling this vent gas. So you saw in the previous video what venting looks like, as the pressure in the battery pack increases as the cells continue to vent, releasing some of that to avoid explosion. And that's impinging on some of these components in the underbody of the vehicle. Okay, so we're trying to control that vent gas and identify any risks posed of impingement onto hazardous components. And the important thing here also to understand is that these two workflows can be combined, and that's done commonly or attempted commonly. But the downside to that is that these physics occur at very small timescales, and they're also very complex. We're talking about things like combustion modeling to really get this right. So there's many advantages to separating these two workflows, especially if we're looking at performing multiple design studies, focusing on the exterior of the vehicle and also the cabin, and the safety of external personnel, then we don't necessarily want to solve for the propagation each time. And that's kind of the focus of this webinar, is how to do that. Okay, so now we're focused on the heat protection and safety workflow. As always, it's important that we're capturing all of the critical physics of the system. In this case, for thermal runaway, we need to capture all of the critical heat sources and also the critical heat transfer mechanisms. So the key ones here, we have the battery pack heat. So we have a fire occurring inside our pack, so it's getting very hot. We need to consider that heat source, and also the heat transfer mechanisms onto the cabin, onto the floor pan, the venting. So again, as we're degassing our pack, this vent gas is very high temperature, very high velocity, and it's potentially impinging on some, um, hazardous components here in the rear of the vehicle. Okay, so going back to this battery pack heat, the most important heat sources are the thermal abuse reaction heats, or the so-called thermal runaway reaction heat. This is taking place in the cells themselves. We also have the heat of combustion. So we're releasing a lot of combustible gases. So there's a combustion heat as well, within the pack. In terms of heat transfer mechanisms, we have conductive heat transfer, so cell to module to pack, and then eventually to our vehicle body. We have convective heat transfer, so the convective heat transfer from the vent gas inside the pack to the various surfaces inside the pack. And of course, radiation heat transfer. So surface to surface radiation, we have some very hot components inside the pack, the modules, but also radiation heat transfer from the flame to the various surfaces. This flame can get extremely hot, very high temperatures. So we're trying to capture all that within our simulations adequately. Okay, so this is a figure outlining at the highest level the thermal runaway heat protection workflow that we have developed. So this coupling is all facilitated via Cotherm. So this is our automation and workflow management tool here at TAI. And the workflow takes a few different inputs. We have our cell level data. So this is transient data of our thermal abuse reaction heat. So our so-called thermal runaway exothermic reactions. And we're placing those directly into our cells. We have our gas phase combustion heat. So both of these, the runaway reaction heat and the gas phase combustion heat, these are a function of the state of charge, as well as the type of cell that you have. We also have venting data, so transient venting data are our cell venting gas temperature and flow rate. And you can get this data reliably from either cell scale testing, so-called ARC test or accelerating rate calorimeter, or with an independent simulation. Okay, the other piece of information we need is some idea of the rate of propagation of thermal runaway occurring in our pack. So as I mentioned previously, we can get this, by resolving these physics and actually simulating this propagation. Again, the downside is, taking a heavy hit to your computational time and also the complexity of your models. So ideally, we have some understanding of this propagation, either, using propagation theory, some semi-empirical propagation models, deriving from, some module scale testing or independent module scale testing, taking place before we do these heat protection workflows. And that's just because, again, we're doing a lot of design studies on the exterior of the vehicle. We don't necessarily want to repeat those simulations each time. We want to cut down that simulation time if we can. So here you can see, putting these together, we can get some, superimposed transient curves of the transient boundary conditions we need for these simulations. We have plotted here. So we're going to be solving a 5-minute thermal runaway event. This is our thermal abuse reaction heat, our runaway reaction heat, and our combustion reaction heat plotted over time. We also get boundary conditions for our venting, so our vent gas flow rate and temperature outside the pack. So this workflow is automated via Cotherm. You can see the Cotherm process template here in the middle. Cotherm takes tabular data as inputs for the thermal runaway reaction heat, combustion heat, and the pack vent temperature and flow rate. So you can see the velocity and temperature, for example, here. You can see the key properties window here. This is where all the user-facing inputs are defined for the process. So the user would pop open the Cotherm process and just focus on these inputs, right? Where this is where you're defining model paths, things like the length of, runaway event you want to simulate, 5 minutes, 10 minutes, 30 minutes. Then you can hit run, and you can perform your transient thermal safety coupling and your heat protection and safety analysis. Okay, the thermal model setup for this demo is described here on this slide. We have a generic EV model. We have a battery pack here. We have 6 modules, hundreds of cylindrical cells within each module, a vent exhaust port, some underbody components, high voltage cables, connectors, motor, inverter, etc. And then again, the important thing here with this workflow is that we're not necessarily trying to resolve the propagation physics exactly. Again, you can, but ideally, we're separating these workflows and we're modeling them semi-empirically. Okay, so the most important thing is that we're capturing all of the important heat rates within the pack and the heat transfer mechanisms within the pack. Okay, so for heat rates, we have our thermal induced reaction heat, our thermal runaway reaction heat, we're placing that directly into the cells. We also have our combustion heat. So this is, the combustible gases released from venting of the cells. So we're releasing this combustion heat into our fluid nodes, our module fluid nodes. We have a network of fluid nodes, one for each module, and then connected via advection links to the pack fluid node and then to the exterior. For heat transfer mechanisms, the first is conduction, so cell to module to pack to the vehicle body. So this is all handled automatically in Titherm with the thermal mesh. We have convection, so from the vent gas to the various surfaces. And then finally radiation. So radiation heat transfer surface to surface. Of course, we have some high temperature surfaces within our pack and also on the vehicle body. This is handled automatically in Titherm, but we're also considering here our flame radiation source. So the radiation from the flame of the fire occurring inside the pack. And we're considering this with an effective heat transfer coefficient. So, essentially gray body radiation between our flame temperature and the surface temperature of the element. So in this demo, the propagation information that we're using derives from the literature. So from an experimental study of 18 650 cells arranged into modules. And here the authors were studying the thermal runaway propagation rate as a function of some various parameters like cell spacing and thermal resistance. So interestingly, they found that the velocity of propagation front was relatively constant. So the rate of propagation really is dependent on where you are, the number of connections in your module. So we're applying these same equations for this demo. But ideally, this data would come from experimental testing with the exact modules themselves or with some independent simulation conducted previously. Here we can see the CFD model used for this demo. We're using star CCM here, but really, coupling with any of the major CFD tools on the market is possible. And you can see some mesh refinement here in the venting region. So we can resolve our, conjugate heat transfer here and the vent gas impingement on some of these components. Coulthurm is applying our transient vent boundary condition here at the vent exhaust port. The plot here is showing this boundary condition, the transient vent gas temperature and velocity again for our 5-minute venting scenario. So again, Coulthurm is facilitating the coupling and the conjugate heat transfer between Titherm and the CFD tool in this workflow. So this is done with our standard thermal CFD coupling mechanism. So Titherm's passing surface temperatures to the CFD tool, and the CFD tool is providing back the convection data. And this Coulthurm process supports both fully transient and stepwise transient coupling schemes. So in the fully transient coupling, both the CFD model and the Titherm model are run fully transient, and then they are passing this information, this coupling information back and forth at a prescribed interval. And this interval can change depending on how you want to resolve the physics and the timescales of the problem. And then essentially with the stepwise coupling, we're trying to cut down the number of CFD iterations because this is the bottleneck. And in turn, we're trying to cut down the overall computational time of the process. So these CFD snapshots are steady snapshots that we're coupling with, but at very small coupling intervals, things like 1 to 5 seconds for thermal runaway, just so we can resolve the physics enough. So you can see the benchmarking results here on this slide. we're comparing the fully transient and stepwise transient coupling schemes for our demo models. So this is for a 5-minute runaway and venting scenario. You can see the fully transient coupling took about 2.5 days, and the stepwise, somewhere between 16 and 17 hours. Okay, dissecting this a little bit further, you can see that the CFD solve is generally the bottleneck here. And that's why we can get so much value from our stepwise approach, simplifying the coupling with steady CFD instances. And the idea here is that the stepwise approach can increase the viability for these longer runaway scenarios. So, maybe 5 minutes is viable and fully transient, but can we run, 10 minutes, 30 minutes with stepwise and then retain sufficient accuracy with that method? So this slide shows the comparison of part max temperature, basically showing very good agreement between the stepwise method and the transient method. So on some underbody components here, so the high voltage cables, connectors, motor, drive shaft. So these are the components receiving direct vent gas impingement from the battery pack. Also on the floor panel, so carpet temperature inside the cabin, external floor pan temperature. This is the surface facing the battery pack directly. Finally, also on the battery pack itself, the bottom cover, the module, and the cell max temperature here. So overall, the RMSD root mean square deviation was just over 2 degrees, which is very good, especially at these elevated temperatures. So based on this benchmark, we can conclude that the stepwise transient coupling resulted in over 3 times speed up and did demonstrate the ability to retain accuracy to a sufficient degree. The Cotherm template also supports automated animation generation functionality for thermal and CFD tools. So for example, on the left, we can visualize the battery pack temperatures as well as in this underbody venting region. On the right, we can visualize the transient flow field from the venting, see how that develops over time, as well as how the air warms around the pack as thermal runaway progresses. Okay, for heat protection analysis with this workflow, we're including a calculation of time at temperature for specific parts of interest. So if you're not familiar with time at temperature, this is a relatively old concept that's developed for durability and life cycle analysis. It's still used for components expected to experience some form of thermal degradation. So what we do with this concept is we start with some test data or historical data from many years of operation with these components, and we're defining some thermal degradation behavior of the component, trying to define some target temperatures that we can look at in our simulations. Okay, so then when we do our drive cycle simulations, either for the ICE vehicle or the electric vehicle, we're extracting parameters like time of temperature at these specified design temperatures, the temperature ranges that are being experienced, the cycles experienced over the drive cycle. For the ICE vehicle, we're generally looking at underhood and underbody components, especially near the exhaust. For the EV, battery and electronics components. Finally, if we combine that with some information about driving habits, we can get some idea of the durability of the component for the entire life cycle of the vehicle. Okay, and we can apply the same time and temperature concept here to assess the short-term durability of components during thermal runaway. And that's based on some information of ignition temperature or degradation temperature. And we can use the simulated time at temperature to then assess also the safety risk posed to vehicle occupants and first responders. So in this particular 5-minute runaway event that was simulated, there were a couple of components identified that did cross these defined targets. And the first thing we can do is we can visualize this in Tytherm, in the Tytherm post-processor. We can see with the design temperature visualization, the parts that exceeded these target temperatures. In this case, we're looking at these high voltage cables downstream of the venting, and then the floor pan, specifically the foam insulation layer within the floor. So for the high voltage cables, the degradation temperature of this PVC insulation is about 200 degrees, and the time at temperature results show that we exceeded this temperature for nearly 1 minute. So this is likely long enough to pose a significant risk of electric shock to first responders. If this insulation degrades sufficiently, especially like a shock risk for firefighters if using water to extinguish the flames. For the foam layer, the ignition temperature of polyurethane foam is about 310 degrees. And we could see we exceeded this temperature for over 3 minutes. So this means that anywhere within this 3-minute period, if the foam were to come in contact with another ignition source, we could potentially have a hazardous situation in the cabin. If we think back to our global safety standards, we likely did not meet our required design criteria of 5 minutes safe egress time for this design. So a significant benefit historically to using Tytherm for these heat protection analyses, especially these long transient simulations, is the ability to perform rapid subsequent design studies in Tytherm standalone. So take our previous example. We simulated a 5-minute thermal runaway event using fully transient coupling. It took about 2.5 days, and we identified some potential flammability risks in the floor insulation. We showed the time at ignition temperature for the floor insulation of over 3 minutes, and maybe in our safety assessment, we identified that this poses too great of a safety risk. Okay, so since our convection data has already been imported into the thermal model, and it's still there, and also because the flow field isn't changing substantially, we can perform subsequent rapid design studies in Tytherm without rerunning or coupling with any safety. So in this example design study, we added a ceramic fiber blanket between the battery pack and the floor pan, and we can see, as a result, the exterior floor pan and carpet temperatures decreased significantly. And the time at ignition temperature decreased to just over a minute. And most importantly, for this assessment here, you could see the computational time was only 6 hours for this rapid thermal design study. So this slide is just an assortment of other common heat protection workflows as extended to the thermal runaway application. And to be clear, these were not benchmarked part of the webinar, but they're still worth discussing. Again, there's a lot of workflows out there right now that range all over the spectrum, of the trade-off between accuracy and simulation time. And these are some that can, cut down the computational time. So in the first box, just pointing out that for some types of analysis, a very quick steady state snapshot of the maximum achieved temperatures can be sufficient. So maybe we're only looking at a few components, or maybe we're only interested in a sensitivity study, comparing the effect of various inputs on some of these maximum temperatures. So that type of steady state workflow is also possible here. And we do see that a lot for underhood, underbody analysis for the ICE vehicles. And that's mainly because the turnaround time for a steady analysis is very quick. Number two, just showing how we can use a single CFD instance also in a transient simulation. So this is done by scaling convection data as a function of some parameter. So for underhood and underbody analysis, this is commonly done with the vehicle speed. So here for thermal runaway, this method is viable for the venting region. So here in this case. So we could scale the convection as a function of the vent gas flow rate. So cutting down the CFD load significantly with the goal of achieving very rapid turnaround times for a transient simulation. And then finally, next two boxes, 3 and 4, just pointing out that this workflow, the template that we have here can also be used for either venting only or pack only analysis if that's desired. So maybe we only know the vent gas information from the pack, so we can focus on that part of the problem, or vice versa. Okay, so just to summarize, we have developed a Cotherm template for transient heat protection and safety analysis during a thermal runaway event. This template enables the user to run either fully transient or stepwise transient coupling schemes, and based on our benchmarking evaluations, we've demonstrated comparable accuracy, very low RMSD, but also significantly reduced computational times for the stepwise method, 3x speed up in this example. Tytherm also enables, the rapid design studies for heat protection durability analysis. So maybe you want to, go forward with the fully transient approach, knowing that, maybe the first run takes, a week for a 10-minute transient, but then, you can perform then rapid design studies using that same flow field if it does not change significantly. And then, of course, Tytherm also enables, a lot of other simplified conjugate heat transfer workflows for quick turnarounds. And these methods have been validated in other underbody applications for the IC vehicle over the years. So there's a lot of potential here for the specific user to evaluate, the full spectrum of computational time versus simulation accuracy and what fits best for them. And I will just tease one more time. This is actually part one of a two-part webinar. So part two focuses on propagation. So a propagation solution using Titherm to actually resolve the thermal runaway propagation occurring within the pack. This will take place on Thursday, August 10th at 9 a.m. So definitely keep that in mind to keep the ideas flowing. And thank you, sincerely very much for your time. We very much appreciate it. And at this time, I think we'd like to open it up for any questions.
All right, thank you, Dennis. And I just in the chat, I posted the link to register for next month's webinar to anyone that is interested. So yeah, let's go to the questions. Let's see. You showed a 5-minute runaway event in this webinar. Can the process also handle longer simulations, i.e. 10 minutes, 30 minutes?
Yes, absolutely. So the Cotherm template you can put any end time you want in there, 5 minutes, 10 minutes, 30 minutes. It really comes down to choosing the method that fits the turnaround time that you want. So between fully transient or stepwise transient, and also depending on what kind of HPC resources you have available to you. But yeah, I mean, sky's the limit.
Okay, thank you. Are the Cotherm template and demo models available for testing?
Yes, we are actually working with a few OEMs now on deployment of this process. So, and this template and along with these demo models is definitely available by request.
All right, thank you. Have you performed any validation studies for these methods?
What I can say about that is that as I just mentioned, we are working on deployment currently, so those types of things are in discussion. But also that a lot of these methods are kind of born from heavily validated, highly successful workflows applied to underhood and underbody analysis for ICE vehicles. So in that sense, yes. But those for runaway application, those things are ongoing.
All right, thank you. Instead of using an empirical model to predict the battery propagation part of the model, is it possible to map results from another Titherm battery propagation model instead?
Yes, that's actually another common workflow that we don't that I didn't explain, but yeah, in terms of alternate workflows. But yeah, a lot of times customers will map either exhaust temperatures from another 1D tool that resolves their exhaust temperatures. But in this case, yes, you could also map surface temperatures from the battery pack from an independent simulation. Yeah.
All right, thank you. Is the process of coupling with CFD codes, in particular with Fluent, fully automated? And are there any restrictions for coupling with Fluent?
There are not restrictions for coupling with Fluent. We have a lot of coupling examples that do that, thermal safety coupling with Fluent. This demo, right now, as it sits, doesn't have Fluent integrated into it, but that's no problem. Upon request, that can be made available, and there's no restrictions that we know of. Yeah. Just based on all the other coupling examples that we have with Fluent, there's nothing in this workflow that is newly developed in that sense.
And I may have missed if you mentioned, was the vehicle stationary or in motion for this study?
It's at idle. So there's some low idle air velocity in the CFD model.
Okay, well, thank you, Dennis. Looks like that's it for questions. So again, thank you everyone for your time and for attending today. We appreciate that. You will follow up and you will receive a follow-up email this afternoon that contains links to download this presentation, the slides, as well as to watch the recorded webinar session. Again, thank you everyone and have a nice day.